Put this to the cloud, and I'll get started. So, first, the introduction homeworks are past due on Pearson's MyLab and Mastering. Your introduction to mastering physics and the physics primer. You can always do them late. The way it is currently set up, for every day you are late, you get 1% off the work you've done. For every day late the work is, you get 1% off the work you do after the due date, up to a maximum of 10%. So you're always going to get at least 90% of the points for doing late work. I did go through, yeah, it's I gotta look over the problem sets again to see if there's anything. The homework that is due, the homework on chapter 1 and chapter 2 is due on, homework number 1 is due on the 10th. Homework number 2 on chapter 2 and chapter 3 is due on the 17th. We're going to be doing chapter 3 today. Because chapter 3 is short. It's just about how vectors. Any questions about any of that? No, I'm going to get started. Oops. So, we're going to talk about vectors in physics. So here are some example vectors. We have a vector A, a vector B, and they add up to be a vector C. C here, you can see how C goes from the beginning of A to the end of B, where A and B are connected head to tail. C is the sum of A and B in this situation. So this vector C you see here is A plus B. So we're going to start by talking about the difference between a scalar quantity and a vector quantity. And the difference between a scalar quantity and a vector quantity is direction. Then we'll talk about how we can break a vector down into its components. Name?
Oh, Gina?
How we can break a vector into its components. We'll talk about adding and subtracting vectors. Then we'll talk about unit vectors, which are vectors of unit length, which we use to designate directions. And they make it easier to do things like write out a vector in component form. We'll talk about particular vectors, the position, displacement, velocity, and acceleration vectors. So we talked about position, displacement, velocity, and acceleration in chapter 2. When we were talking about the kinematics of stuff, we're going to talk about how we can represent them as vectors and thus how we can expand from 1 dimension to 2 dimensions. And chapter 4 will be about 2-dimensional kinematics. Then we're going to talk about relative motion. So when we talk about relative motion, that's a way you combine vectors. So a scalar is a number with a unit. A vector is a quantity with a magnitude, a size, and a direction. So the difference between a vector and a scalar is a direction. So the distance you travel is a scalar quantity. You traveled 5 meters. You traveled 5 meters north, that would be a vector. So here you can see we have several vectors, if you know, for example, if you want to get to the library from wherever you are, you know the library is half a mile away. Well, you need to also know what direction the library is half a mile away in. Otherwise, there's a whole circle of places the library could be. So here, if you're here and you're going 0.5 miles, you can go this way, you go this way, you go this way, you go this way. The library could be any of those places. So you need to know how far and which way. For lots of other things, it's lots of other quantities we deal with, they have a direction. So velocity has a direction, acceleration has a direction. Name? So to figure out where you're going, you need to know how far and which way. Vectors have a size and a direction. And it might be that you can't go to the library in a straight line. That you live in a city like Chicago and everything is on a grid. So you might have to go some direction along one axis and some direction along the other. These would be the components of this vector. If I want to get from here to here, I have to move so many blocks west and so many blocks north, 3 blocks west and 3 blocks north. So I can break a vector down into its components. So it's very useful to break vectors down into their components and say the x direction. If you define 2 directions, x and y, that are perpendicular to each other, you can break your vector down into the x direction and the y direction and work with each component separately. And often this is useful because often you might have, say, an acceleration that's only in one direction, like gravity is down. So it's in the negative y direction, let's say. If your acceleration is only in the negative y direction, it's helpful to split your starting velocity into its x portion and its y portion and treat them separately. So you can resolve a vector into the perpendicular components using a 2-dimensional coordinate system. So if you know the length of the vector, the magnitude of the vector, and the angle of the vector, usually the standard form measures, when we talk about angle of a vector, we measure counterclockwise from the positive x-axis. That's just the convention. In theory, you could measure other ways. When they talk about bearings or directions, it is actually measured in a different way for angles. But for this course, the standard way for mathematically, the angle is measured from the positive x-axis counterclockwise. And by using some trigonometry, we can find the portion of r in the x direction and the portion of r in the y direction. So if r has magnitude 1.1 meters, and it's at an angle of 25 degrees, r sub x, the r component of x will be 0.997 meters, and the y component of r will be 0.465 meters. We can split it into its x portion and its y portion. And the length, angle, and components can be calculated from each other using trigonometry. So the general thing is, if you know the angle, if you know the magnitude and the direction, the x component is the magnitude times the cosine of the angle. The y component is the magnitude times the sine of the angle. So this lets you break down into x and y components. You can also do the opposite. So this is all just trigonometry. You're dealing with triangles. If you have a triangle with sides x, y, and r, and you have the angle theta in the corner down here, as drawn, the sine of theta will be y over r. The cosine of theta is x over r. The tangent is y over x. So the opposite side of the hypotenuse is the sine, that's y over r. The adjacent side of the hypotenuse is the cosine, that's x over r. And the tangent is the opposite side over the adjacent side, that's y over x. And then if you want to find r from x and y, you can use the Pythagorean theorem. X squared plus y squared equals r squared. So if you want the components, ax is a cosine theta, ay is a sine theta. That's how you go from magnitude and direction to components. To go the other way, to go from components to magnitude and direction. Magnitude is square root of ax squared plus ay squared. And the tangent of theta is ay over ax. So if you're going from length and direction to x and y components, you'll use these equations. And if you're going from x and y components to length and direction, you'll use these equations. The other equation is that the inverse tangent of ay over ax equals theta. There is one slight issue with this equation. So it turns out inverse tangent, if you use it in your calculator, it'll always give you an angle between positive 90 degrees and negative 90 degrees. Because it turns out there are two angles that have the same tangent for any tangent. So it always gives you an answer in this half of the coordinate plane. The solution is, if your x component is negative, you have to add 180 degrees or subtract 180 degrees. That's all. It's just if your x component is negative, you're going to be in this half. You'll have to add 180 degrees or subtract 180 degrees to your angle. It doesn't come up that often. And it should be obvious, like if you're pointing in the negative direction, the angle won't make sense. You just need to think about it a little bit. You might have to add 180 degrees. Or subtract 180. Any questions about these formulas? Just remember to be careful when you're working with negative x components. This will not, you'll have to add or subtract 180 degrees to the theta. It's just because tangent as a function, there are two angles that give you the same tangent. So inverse tangent only can give you half the angles. Because it's got two possibilities, it's got to choose one. Because angles pointing in opposite directions give you the same tangent. Sure. So here's the signs of the vector components. If x is positive and y is negative, it's down here. If x is negative and y is positive, it's up here. If x is negative and y is negative, it's down here. And if x is positive and y is positive, it's up here. I have no idea why they organized it in that order. But most of the time, like a lot of the time in problems, just because it's convenient, Probably the majority of problems will be in this domain. Or this one. So here, what are the components of a 3-meter vector at 30 degrees from the horizontal? So we're going to go through this. What we know our magnitude is 3.0 meters. We know our angle is 30 degrees. We want to find AX and AY. AX is A cosine theta. AY is A sine theta. So AX is 3 meters times the cosine of 30 degrees. AY is 3 meters times the sine of 30 degrees. So 3 times 0.866 or 2.6 meters. And AY is 3 times 0.5 or 1.5 meters. Actually, I made a small mistake on this right up. I should have done this to 2 significant figures instead of 3. But that's easy enough to fix. Quick. Delete. Any questions about that? Should be reasonably straightforward. And these slides are up on Blackboard. Here we have a little more complicated problem. We have a neighborhood zip line is set up from a large tree to the ground, and the zip line makes an angle of 18 degrees with the horizontal and is anchored to the ground 12 meters from the base of the tree. What is the height of the top of the zip line above the ground? So the other important thing for this is to remember that the tangent of theta is AY over AX. And what length of wire is needed to make the zip line? A couple of minutes to work on this, but think about what you know and what you're being asked. That's, I just uploaded the PowerPoint. It's not a PDF like the other one was. So it might be that. It's actually a PowerPoint that I put out. I'll try and add PDFs of them for the future. Sorry. And you should be, I don't know, it might be because you can't open a PowerPoint or something. And I can. Try and quickly add. Chapter 3. There should be a PDF version of them up for now. Slides for chapter 3 with several attachments. I just added the PDF of the ones with the word problems. Hopefully that will work. I'll go through and do that for the other ones tonight. Why does this always happen? Oh, so for this, click. So we have our tree. So what do we know? We know Rx is 12 meters, this distance here, and our angle theta is 13 degrees. What do we want to know? Well, for part A, we want to know what Ry is, the height here. For part B, we want to know the length of the wire, what R is. So for part A, to find the height, knowing Rx, trying to find Ry, and knowing theta, we could use this equation. We want to find Ry. The tangent of theta is Ry over Rx. So Ry is Rx times tangent of theta. So Ry will be 12 meters times the tangent of 18 degrees. Apparently I messed up the ordering of the animations. Well, I'll just go through this. Then for R, well, Rx is R cosine theta. So R is Rx over cosine theta. So R is 12 meters over cosine of 18 degrees. So Ry is 3.9 meters and R is 12.6 meters. And I did that to more significant figures for the length of the wire because it's just clearer that way. Yes, that would be rounded to 13. Generally, it's look at the triangle and figure out the trig. Is how you deal with a lot of these situations. And before I forget, I'm going to fix those animations. Easy fix. I just, oops. That. Hey, everybody got this? Sure. But yeah, so if you know Rx or Ry and the angle, you can often figure out, if you know the angle at one of the three sides of the triangle, you can figure out the other ones. So it's not uncommon to go from the X component and the angle, and you want to find the magnitude or something like that. Okay, I'm going to continue on. Now, there are two main ways you can add vectors. The first is graphically. You can take each vector and place them head to tail. There's some problems on the homework where you're going to do this in the interface, where you have like vectors that you need to put head to tail, and then when you add them, so here we have A, B, and C. You can think of them as things you're doing sequentially. And the sum is A plus B plus C. It goes from the start of A to the end of C. And you connect them all head to tail. So the sum points from the tail of the first to the head of the last. And you hook them all up head to tail when you do this graphically. This is a way to get like a drawing of it, but it's annoying to get numbers out this way. It's awkward and hard to deal with. So you can also add vectors with components. And this is straightforward. You add the X components together, you add the Y components together. That is your sum. The X and Y components, you add them up separately, and that is your resultant vector. If you're not asked to write it as magnitude and direction, you just leave it in X and Y components, like on a test. If you are asked to do magnitude and direction, well, this will allow you to convert your new vector back to magnitude and direction. So there's sort of two approaches. You can draw them and connect them. And here you can see the individual components, AX, AY, BX, BY. So CX is AX plus BX. CY is AY plus BY. And that allows you to work out C. So most of the time when you're doing calculations, you will be adding components. To subtract vectors, well, if you do it graphically, when you subtract something, you add its negative. The negative of a vector is a vector of the same length pointing in the opposite direction. So here, A plus minus B is D. This is B, this is minus B. If you're doing it with components, you subtract components. So dx will be ax minus bx. dy will be ay minus by. So here we have some vectors with names. We have A, B, C, and D in the ordinal directions, up, down, left, and right. And then we have E, F, G, and H. These are diagonal, and they're equal in length to the diagonal of this square. So if I moved E over, it would go from here to here. So what vectors are the following quantities equal to? So A plus B. What would I get if I added A plus B? Which of these letter vectors would I get for A plus B? So when we add vectors graphically, we connect them head to tail. So A plus B would be a vector like this. So it's capable of drawing a straight line. So that would be A plus B. So what vector is that? Yes, it is up. So here we have D minus A. What do you think that would be? Yep. So D, this is minus A. So that is D minus A. We have G minus C. What would that be? Yep. So G, then we have minus C, which is going this way. That's minus C. And this going straight down is G minus C, which is B. And then lastly, we have B plus H minus D. That is also correct. So here, we just sort of go on the path, B plus H minus D, and that would be G. Erase what I have sketched on the board. Any questions about these? So, unit vectors are the vectors we use to talk about what directions are. So the most common ones we're going to use, unit vectors are dimensionless vectors of unit length. So basically they're a thing. If you multiply a scalar by a unit vector, you'll get a vector in that direction. They're a way to talk about a direction. So the unit vectors we're most commonly going to use in this course. In unit vectors, instead of having an arrow on top, so you know how the vectors have had arrows on top to indicate their vectors? Unit vectors have a little hat on top. So the vectors we're going to use for this course are x hat and y hat. And if you see them used in other contexts, you might see them as I hat and j hat sometimes. They're just different names for the same sort of things. But we will be using x hat and y hat, which are a lot more intuitive because the actual names of the axes. There are some other unit vectors. We won't be using them super often, but like there's r hat, which is a radial vector. Doesn't come up that often. But unit vectors are dimensionless vectors of unit length. And they're useful because they're a tool that lets, with unit vectors, we can write out a vector in component form just as a sum. So if we have a vector of unit length and we multiply it by a scalar, the multiplier changes the length. So if we have a here, this is 3a, and this is negative 3a. So a minus sign will indicate the direction. So if we have our unit vector in the x direction, if our vector has a positive x component of like 5, we'll put 5 times x hat. If it has a negative x component of like 3, it'd be negative 3x hat. So it lets us write, instead of having to say ax and ay, we can just write it out as, for some given vector that has components ax and ay, a vector will be ax times x hat plus ay times y. So here are some examples. We have some unit vector, some vectors written with units. We have 1 meter times x hat plus 1 meter times y hat. So again, remember that the stuff that's times the x hat is its component in the x direction. The stuff that's times y hat is its component in the y direction. So which of these vectors has the same direction as 1 meter x hat plus 1 meter y hat? Just as an indication, I'll draw over here. This is x hat. That's y hat. So which of these is pointing in the direction of 1 meter times x hat plus 1 meter times y hat? So here, yes, x component is positive, y component is positive. That's B. Plus 1 in x, plus 1 in y. B. How about 1 meter x hat minus 1 meter y hat? C is correct. Minus 1 meter x hat plus 1 meter y hat. I think I heard A, which is correct. And then if both are minus 1 meter x hat, minus 1 meter y hat, that's D. All this is writing out the components. It's a way to write out the components, but as a sum. And often it's just more convenient to be able to write it all out in one line like that.
Wait, I'm confused on the direction thing, like the quadrant,
Yeah, so if x is positive and y is positive, B is in the first quadrant.
Okay.
If x is positive and y is negative, x is positive, y is negative, C here. And then for this one, x is negative and y is positive. That's A. And the last one, X is negative and Y is negative. Oops. Let me quickly fix this. This got messed up by the resizing. Um, so the position vector, RF. It's the final position, points from the origin to the location in question. So if you want to talk about a position as a vector, it goes from 0 to wherever the position is. The displacement vector is final position, it's RF minus RI, final position minus initial position. So it points from the initial position to the final position. And it is actually defined, delta R here is RF minus RI. So that's position and displacement. So delta R equals R final minus R initial. Our average velocity is delta R over delta T. You'll notice that these are basically the same as the equations we had for velocity in one dimension, just instead of using X, we're using the vector R. So your average velocity will be in the same direction as your displacement. Your instantaneous velocity, well, it'll be tangent to the curve. So the instantaneous velocity will end up tangent to the curve as displacement and time get smaller and smaller. So your instantaneous velocity will be along the tangent line of the curve you're on. Let me move this out of the way. And the average acceleration vector is just change in velocity over delta T. And if you want to do those with calculus, all you need to do is, take the derivative of the x, take the derivative of the y. And that'll give you the velocity in the x and the velocity of the y. The average acceleration is the direction of the change of acceleration. So initial velocity minus final velocity over delta T. The velocity vector will always be in the direction of motion, and the acceleration vector can point anywhere. If you want the fancy multivariable calculus, it points in the direction of curvature, but yeah, it can basically point anywhere. And that'll determine the shape of the path. But there is no restriction on the direction that it can point. Okay, we're gonna keep going a little further. Um, so here we have a problem. We have a dragonfly that is initially at the position. Our initial is 4.6 meters in the x direction and 0.96 meters in the y direction. 4.6 meters x hat, 0.96 meters y hat. After 3 seconds, the dragon flies at the position 0.52 meters x hat, 0.24 meters y hat. So what is the dragonfly's average velocity during this time? So dragonfly is moving from initial position to final position. Delta R will be final position minus initial position. And average velocity will be delta R over delta T. So, what do we know and what are we looking for? We know the final velocity and the initial velocity, which in order to save space, I'm not writing them out. And we know the time is 3 seconds. And we want to find, the final position and the initial position. And we want to find the average velocity. The average velocity is delta R over delta T. So it's RF minus RI over T. So that's 0.52 meters X plus 0.24 meters Y minus 0.46 meters X plus 0.96 meters Y, all over 3 seconds. So first, we combine like terms on the top. We combine the X's and the Y's. We get negative 4.08 meters X and 1.44 meters Y. And that's divided by 3 seconds. So then we divide each term by 3 seconds. So we get negative 1.36 meters per second X and 0.480 meters per second Y. So this boils down to you find the X component and the Y component of velocity. The X component of velocity is going to be X final minus X initial over time. The Y component will be Y final minus Y initial over time. Hardest part about dealing with vectors is just to get lots of numbers. It's not like calculations are hard. There's just a lot of them because you have to do everything for X and everything for Y. What we got through? So here, we want to find the speed and direction of motion of a trout with velocity v. Speed, that's the magnitude of the velocity. Direction of motion, that's the direction of the velocity. So I'll let you work on this for a couple of minutes. So speed is just the magnitude of velocity. Magnitude of velocity is going to be the x component of velocity squared plus the y component of velocity squared. Just take the square root. The x component is 2.6 meters per second, because we know that. Y component is negative 1.9 meters per second. So 2.6 meters per second squared minus 1.9 meters per second squared. And that equals 3.2 meters per second. Because that ends up positive. So that's the speed. The direction is the angle. That's going to be the inverse tangent of Vy over Vx. So the inverse tangent of minus 1.9 meters per second over 2.6 meters per second cancels. The angle is, that is wrong. Negative 36. So the angle is negative 36. It's 36 degrees below the horizontal. Must have been, I dropped the minus sign in there somewhere. I will re-upload these slides with all the corrections I've made. You look at this. So here we have a car that's traveling with an initial velocity of negative 6.36 meters per second x and positive 6.36 meters per second y. And 8 seconds later, the final velocity is positive 15 meters per second y. What is the average acceleration of the car? Remember, average acceleration is final velocity minus initial velocity over time.
this formula for average formation?
Change in velocity over time. So final velocity minus initial velocity over time.
Okay.
This one, delta V. So that's gonna be final minus initial. So. What we know final velocity and initial velocity. We know time is 8 seconds. We're trying to find average acceleration. So average acceleration is final velocity minus initial velocity over time. So if we plug in our values, our final velocity is 15 meters per second in the y direction. Our initial velocity is negative 6.36 meters per second in the x direction and positive 3.66 meters per second in the y direction. So if we combine our x's and y's up here, minus negative 6.36 gives us positive 6.36 meters per second in the x direction. And 15 minus 6.36 gives us 8.64 meters per second in the y direction. That change occurs over 8 seconds. We're going to divide each of those by 8. And so we'll get 0.795 meters per second squared in the x direction and 1.08 meters per second squared in the y direction. And this doesn't say you have to put it in magnitude and direction, so you can stop here. You could if you wanted to, but you don't need to. And that is where we're going to stop for today. So we have a little bit of chapter 3 to finish up, and then we'll start chapter 4 tomorrow. So that was vectors. And I will re-up these slides with the corrections on them. I'm going to stop sharing and end the meeting.